of today's lesson. The first side is a mathematical side. So we're going to talk about some calculations dealing with gases. The second side, though, is we want to make sure we understand the molecular side. So keep in mind 3 sides of the triangle, right? On Fridays, where we'll kind of get the macroscopic side, because we'll go into the lab and do some experimentations with gases. But we want to make sure that you don't want to just memorize the mathematical processes here. Understand what's happening at the molecular level at the same time. So this is my vision of gases. It's simple, but it's what I use. If you have another one you want to come with, that's fine, but you need to have a picture when you think about gases. I literally imagine bouncy balls, right? Tiny little bouncy balls flying through the air, bouncing off the walls, bouncing off each other. Like that's what it would look like if I could see the air in this room. Okay? Now, another thing is understanding the concept of pressure. Because pressure is a key important thing with gases. So in case you've never learned about pressure before in other classes, pressure is a measurement of force per area. We won't ever calculate pressure in this way because we just measure it with devices. But it's important to recognize what that unit is telling you. So the unit of pressure is telling you how much force is being exerted in relation to how much space there is. So it's a 2-unit variable, or it's dependent upon 2 things. Meaning, if you change one, pressure will change, even if the other does not. Okay, so pressure is affected by how often the bouncy balls hit the walls and how hard they hit the walls. Because the area is like how often, right? Because if you have a lot of area, they're not going to hit the walls very often. If you have little area, they'll hit the walls a lot, right? So if we could magic school bus into our balloon that I blew up here, right? The pressure, the reason why balloons take this shape is literally because the gases inside are bouncing and hitting the walls of the balloon, right? Now, we also have something known as atmospheric pressure, which is the pressure we feel and have here on Earth. Does anyone know what atmospheric pressure is? Yeah, Zach?
Isn't it 14 something? It's like the actual atmospheric pressure of Earth, like where we think.
Oh, yeah, sure. I was thinking more just like, what is it, not the number of it? Like, what is that number measuring?
It's like just like the pressure we feel of like the air.
Yeah. Right, so I want you to kind of think about it maybe, I read this once, I can't take credit for this analogy, but I really liked it. When you think about atmospheric pressure, right? Okay, so here's a cute little mountain. Here's us. Okay. When we're at sea level is classified as 1 ATM, 1 atmospheric pressure. Okay? As you go higher in elevation, what happens to atmospheric pressure?
It goes down.
Decreases.
Yes.
Okay? You could pretty much imagine that we live in an ocean of air. Okay? Think of this as an ocean now. Where this guy's at the bottom of the ocean, so he feels the greatest pressure. As you climb up the mountain and get higher in elevation, there's less pressure because there's less air pushing down on us. Now you can actually feel this. Ready? We're all going to look silly together. Take your hands like this. Everyone join me. Ready? And go like this. You can feel the ocean. You feel it? Okay, you saw now. But if we were to do this at sea level, what would we feel?
Oh, more.
More, right? And if you did it on top of Mount Everest,
You'd be like, nothing.
right? It'd be even less, right? So imagine that's literally like the way you think about air, think about the pressure around us. Kind of cool side connection, I guess, to this, but just kind of cool to see how like it is affected. This is why, like as runners, like if you run or know someone who runs, if you go run in California and you normally live in Utah, we get really excited. Why?
Because there's just more air to breathe.
Yeah, there's more oxygen, but our bodies are used to less, And so typically you can run a lot faster. Like my fastest times in college were all run at sea level. They weren't ever run here in Utah because it's easier for us. Vice versa, people who live at sea level and then go somewhere at elevation, they struggle, right? And that's why like professional teams will travel like weeks before to adjust to the elevation. So in Oregon, there's the Nike track team, distance running team, and they literally have made these houses that simulate that these athletes are living at like 10,000 feet.
That's pretty cool.
But it's in Oregon, so it's at sea level. But then it conditions their body to learn how to use less oxygen and be efficient with it, which is kind of cool. But anyway, so kind of just cool as we're thinking about pressure. Okay, this equation that I'm about to show you is on your formula sheet. You guys all, I gave you one of those, right? Yes? Okay, well that, we haven't used them yet, but this unit, we're going to start using it and it'll be helpful. So you don't need to memorize these equations. You just need to know how to use them. If you want to pull out your formula sheet right now though, it might be helpful just to see it. So when you do take the test on this unit, you like know where to find these numbers and things like that. Okay? Did anyone not get one of those because you missed that day? Anyone not get a laminated formula sheet? Being that we're taking our test at home, you'll definitely want one. Okay. Okay, so this is known as the ideal gas law, and the equation is pressure times volume is equal to moles times this constant R times temperature. It's under the section on your formula sheet labeled gases, liquids, solids, or solutions. It's the first equation up there. Another fun fact about your formula sheet to get familiar with, the way it's set up is this side, the left side of the paper is all the formulas, the right side are all the variables. So if you even forget, because sometimes on tests we forget simple things, and you're like, oh, what does P stand for? It tells you right here. Okay? Now the R value is a constant, meaning it has a mathematical value determined already by scientists, but that value changes if the units change. So you'll see if you look on your notes, it's also on your formula sheet, but I've given you a list of the different values R can be. Depending on your problem, depends on which R you pick from this list. The biggest thing is the units are what we want to pay attention to. We'll do 2 problems here in a second where we'll practice doing that. Okay? I lost my train of thought. People in the hallway distracted. Okay, let's try a problem. Oh, let's talk about it and then we'll try a problem. Oh, also side note so you don't freak out. I didn't come up with this. It's just the way I learned it, and so since the way I learned it, it's the way you learn it. So you're welcome, I guess. But it's kind of a chemistry inside joke type thing. I don't know what you call it, but we often call this equation the perv-nerd equation. And if you read it, perv-nerd. So if you hear me say perv-nerd, I'm talking about this equation.
All right.
That's just, you'll know what I mean and not freak out, right?
Yes.
Okay.
Why not?
Okay, so this is the ideal gas law. Okay. Now, when we use this term ideal gas, these are hypothetical technically. We're making 2 assumptions when we use this equation. The 2 assumptions we're making kind of go to what Taylor and Max brought up of why intermolecular forces aren't a thing with gases. We're assuming, using this equation, that gases have no interactions with each other. Which is mostly true, but not 100%. Because every once in a while, those flying bouncy balls can link up momentarily with each other. The other assumption we're making is we're assuming that the gases themselves, like the bouncy balls, take up 0 space. Which is false because they're matter, so they take up space. But it's kind of a comparison thing, right? It's kind of like in this room right now, let's just say for analogy's sake, if I just had 2 bouncy balls, Compared to the size of this room, do the bouncy balls take up space?
No.
Not really, right? Like they do, but in comparison, not. So those are kind of the two assumptions we make about this. So technically, this equation isn't correct when you use it for any real gas. But it works really, really well unless you're doing the most accurate of work. So that's kind of a weird thing because as chemists, we continue to use this law, which based on a hypothetical perfect gas, because it actually still gives us good information. That's kind of what it means by the ideal gas law. Okay? All right, here's a problem. Let's try it out. So it says calcium carbonate decomposes upon heating to give calcium oxide and calcium dioxide. A sample of calcium carbonate is decomposed and carbon dioxide is collected in a 250 milliliter flask. The gas has a pressure of 1 atm at a temperature of 31 degrees Celsius. How many moles of CO2 are generated? Now, going back to problem solving, the first thing you should do in this problem is circle what are you trying to find.
The moles
Do that
of
now. Circle what you're trying to find. If you circle the word moles of CO2, give yourself a smiley face, because that's what we're trying to find. Okay, chemistry problems can have lots of information, and so you need to make sure the first thing you do is identify what am I even trying to go, or what am I trying to do. Second thing is let's underline all the information and pull out what we know. So someone shout out, what information does it tell me about this thing?
231 degrees.
Okay, so I got a temperature. Let's pull that out, 31 degrees. Good, I know my pressure.
Volume, yeah.
Good. Now, it is important to note, the problem says that we just collect it in a 250 flask. Why does that correspond to the volume, though?
Oh, because gases, you know.
Good, because gases fill the space, right? Technically, though, if this was a liquid, right, that wouldn't be true because they don't fill the space. Okay, so I have a T, I have a P, I have a V. What are we trying to find? N. So we got everything we need.
Wait, what's R?
So R is a constant already given to us. We just got to pick which one to use. So the first thing I do here is this is my preferred way of solving problems, is I like to move the letters around first and then plug in the numbers. So the letter I'm trying to find is what? N. Okay, so mathematically, how do I get N by itself? Very good. Good algebra skills, everybody. So N equals PV over
I didn't think about
RT.
Oh, how easy is that?
what that makes things so much easier.
I know, that's nice.
Now we can plug things in. Now the biggest thing or the trickiest part with using Pervner is making sure the units match the R value. Now the R value is mostly dependent upon the pressure. So my pressure is an ATM, so look at your list of R's, and we want to pick the R that is measured in ATM, which on your yellow paper is the very first one listed. So I'm going to point 0.08206, is that what it is?
Yeah.
The R's are once again on your formula sheet as well, so you don't have to memorize these numbers. You might by default, just because that's what happens when you use something in this, but. Okay, the units are liters times ATM over mole Kelvin. Keep all your units in the problem so that you can make sure it's going the right way. Okay, if I ever draw, do you see how there's like a bright light because of the projector reflecting?
Yes.
Don't let me ever write anything important on that bright light because it doesn't ever show up on the video screen.
Okay.
And it's causing a few issues with some people at home. They keep emailing me like, wait, what? Okay, so there's our R value. So now we need to make sure that P, V, and T match these units. So pressure is the same, so I can plug that in, 1.3. Okay, so there's my P. unit does my volume need to be in?
Liters.
Needs to be in liters because that's what the R is.
So we could times it by 1,000
Currently it's in milliliters,
or divide by 1,000.
divide by 1,000. Or move the decimal 1, 2, 3. 0.250 liters. There's my volume. Temperature, what unit does temperature need to be in? Kelvin. Yep. So currently we're in Celsius, we gotta get it into Kelvin to match.
Plus
Okay. So we're gonna add 273.15 to get it to Kelvin. This is also somewhere on your formula sheet. Or at least that 273.
yeah.
It's under gas.
ST.
Is it under gases as well? Oh, yep, right there at STP. So if you ever forget, there it is.
Is that 2 or 4?
So what is that, 304? Just a scientific side note, if I haven't mentioned this before, the reason why we have to get into Kelvin is because Kelvin technically, well, mostly doesn't go into the negative scale. And using negative numbers mathematically is going to throw things off, right? Like, because you can't end up with negative moles just because your temperature is negative. That wouldn't make any sense. So that's why we always have to convert it into Kelvin. Second thing is when you talk Kelvin and write Kelvin, notice there is no degree sign. Right? So when you talk about Kelvin, it's 273 Kelvin. You don't say 273 degrees Kelvin. For whatever reason, you don't use that on the Kelvin scale. So, okay, questions on the seventh, anybody? Where I got these numbers? Okay, for a smiley face, plug it into your calculator. Let's see if you get the right answer.
Where's my calculator? Come on.
Yeah. Every day around this time, I get the most random phone calls from some state somewhere. I never answer it, but that one is from North
My
Carolina.
calculator just died.
Or they're telling me how to vote. That's how they're trying to do it.
Oh my gosh.
Plug it in. It's good to practice plugging these things in. Make sure you understand the mathematical side. Do you want a calculator?
Can I plug it on my phone? Or,
Yeah, is your calculator dead?
yeah.
Yeah, that's fine.
okay.
I have one too, you borrow one, but anyone else want to borrow one? Isaac?
My phone really gonna die on me.
Check with your table buddy once you get an answer, see if they match. Don't look up here if you don't want to know the answer yet, but if you have your answer, you can compare it with mine.
Yeah.
Okay, something made it wrong because that doesn't make any sense. I got assumption wrong.
Yeah, try it again. Maybe you're you.
I did put one. I'm never wrong. Oh, because time is
It'll be about
or oh, they do matter, right?
Well, because she said, I did like that. I've been being something.
I had a feeling you need to charge my calculator last night.
Yes, if you got the answer that I got, you can give yourself a smiley face. Questions on this problem?
I
Yeah.
needed to charge my calculator last night.
Oh, good question.
Sick day.
It's been a while. We haven't done math in a little bit. So just remember sig fig. So the reason why I rounded it like this is because of significant figures. Now keep in mind, if you got, what did you get if you kept going?
0, 2, 8.
Okay, so if you have that, you're still right, you can have a smiley face because you have the right math answer. If it was for sig fig points, that's where you'd be in trouble. Now keep in mind, it's not something, sig figs aren't something you stress about, we'll just kind of keep practicing all year, and they'll be fine at the end of the year. But the simple rule is this, you go to your equation, this big guy, and you go to the number that has the least amount of significant figures, which would be my pressure of 1.3. It only has 2 sig figs. So my answer only gets 2 sig figs. Because zeros in front aren't significant. So good reminder that. Any other questions? Oh, have a second smiley face if you remember to label your answer.
I don't get a second.
Yes.
Okay? All answers need a label of what's measured and what it is. Okay, give your numbers meaning, because they have meaning. Okay? Questions? Okay, now I want you to notice something here, everybody, with this equation. Okay, give me your eyes up this way. When you track the units, everything should cancel except for the unit you want. So if I notice in my problem here, and it's going to be based off of R, units cancel when they're in opposite places, right? So I have an ATM on top of my fraction, and this ATM is on the bottom of the fraction, or because it's a big fraction, so that cancels away. Liters is on the top, liters is on the bottom, so that cancels away. Kelvin on the top, Kelvin on the bottom. So the only unit left is the unit I want. Tracking your units can really help you make sure that you did things right. There were times in college where I was like, shoot, I don't remember this equation. But by setting up units, I figured out what the equation needed to be. Because I knew what needed to cancel and what needed to be left. So, yeah, take a
So on the formula sheet,
Yeah.
it doesn't have the 0.15 for Kelvin.
Oh, it doesn't?
So do you still want us to do that, or
It does. There's 2 different places where it's at.
Oh, interesting.
on
I would say since I see what you're saying, so down here at STP it's there, but in the actual equation, I'd say that you don't have to. Because this is the AP formula sheet, so. Yeah, good observation. I didn't even notice that, Taylor. I was just going off of what I remember.
Oh, it does have that.
But yeah, so down here it tells you like accurately what it is. But since this equation literally tells you without, I'd say you don't have to have it. Yeah, that makes it a little easier, right? Less writing.
The college board. Student. Yes.
Okay, what other questions, comments on this problem? Okay, let's try the next one. Okay, so fun fact, did you know that tennis balls are often filled with nitrogen gas?
Why? I did not know that.
It helps them so they actually bounce better.
To be honest.
So let's calculate the pressure inside a tennis ball. Okay, first thing, let's read the problem, and if you can circle before I do what we're trying to find, you can have a smiley face. So circle what is the thing we're trying to find. I've already told you, but if you circle that, pressure, have a smiley face. Okay, let's pull out what we know. So get our variables here, so I know volume. Okay. What else do I know here?
Temperature.
Good, I know temperature. What else do I know?
It's the volume.
Do we? So I got my
You
volume,
got volume.
I got my temperature.
How much gas?
Good, I know the amount of it, but what unit is it in?
5 grams.
Grams. So,
No.
Bryce is so excited because we get to change it to moles. It's not that bad, Bryce. What do I do? How do I go from grams to moles?
You have to
just-
multiply it by like the
The thing, so this one.
Good,
goes
so everyone look at your periodic table, find
0.014.
nitrogen, double it because it's N2. Now, does the mass go on the bottom or the top?
Bottom.
There you go. So it's 28.02 us back to what we learned at the beginning of Unit 1, right? Plug that in, we get something. Someone shout it out if you have it before I do.
0.01177.
Like that? Okay, so there's our moles. So let's take our equation and rearrange it. So we have PV equals nRT. What variable are we trying to find this time?
Pressure.
Pressure. Pressure is going to equal nRT over start with your R constant first. Pick which R because then you'll know what you need to convert. So in this case, I'm finding pressure. So it's a little bit up to you because they didn't tell me what unit they wanted. I would by default always go with ATM. So I'm going to use the same R we did before. Okay, so I know my moles, so 0.0117. My R value is at 0.08206.
Isn't the volume in centimeters cubed though?
Good, so we got to convert the volume to what unit?
What do we do with liters?
Yep, to liters again. So this is a very, I don't think this one's on your phone machine. It's pretty simple, but it's very, very helpful. Is that 1 milliliter is equal to 1 centimeter cubed.
Oh.
So literally this is just the same as 144 milliliters.
Which is
Which in liters would be,
0.144.
there we go. Okay, so we got our volume. What do I have to do with my temperature?
Kelvin.
Good, so we gotta convert that into Kelvin, so add 273. So what's that, 297? All right, plug that all into your calculator and see what you get. Yeah.
Could you explain how you got the R constant again?
Yeah, so the R, the one that you pick, so there's just that list of them, right? Is really based off the pressure. In this case, since we're finding pressure, you could pick a different R, kinda. But it's really kind of also based off the unit. So if we look at like the formula sheet options, so the first R value on the form, are you looking at formula sheet or notes, which one you want to look at, formula sheet? So it says 8.314 joules turns mole Kelvin. So what I kind of do is I look at this problem and say, okay, there's nothing about joules in this problem, so that's not the R I want to use. The other two, with the ATM or torr, either of them would actually be acceptable in this problem. The difference would be how you report your answer, right? You'd either say this is in torr or this is in ATM. But since they didn't tell me what unit they wanted, you'd actually get points for both.
Okay.
Does that help?
Yeah.
If pressure's in the problem, then that normally makes it really easy to know what we're doing. So, and I'll be honest, that first R, we won't use this entire unit, because it doesn't deal with gases, it deals with something else later. So, good question.
Okay.
Any other questions? Okay, if you got an answer of, I think if I remember it's like 1.998, which based off sig figs technically means 2.00. No. HEM of nitrogen, you can have a smiley face. Yeah, Carly.
I got 1.98.
Yeah.
This is 1.981.
Oh, oh,
I got 1.98.
you got 1.981.
I got 1.9802.
Yeah, 1.9802.
Oh, so here's the difference. So you're right. We're both right. I was just recalling from memory from last period. And last period we kept the 0.15. So that must have made just the slightest of difference because it actually last time it rounded up to 2.00. But for you guys then, ignore that. This is the right that we want. So 1.98 because the next number was a 1. Is that what we said?
Definitely, there's just one of these.
Yeah, I did.
How does the Kelvin and moles cross out in the equation? Aren't they in the same level?
So, they're both on the, so there's big fractions and little fractions, right? So they're both on top of the big fraction, but within the little fraction within it, the mole's on the bottom. Because this is a fraction too. Do you see that? So like that's how the mole and the Kelvin makes. So you have like a little fraction on a big fraction. So great question though, yeah, 'cause that's a great thing to track. Is what's happening for those units. So, any other questions with using? Anyone not get that or have other questions with that?
Wouldn't for the moles, wouldn't it like the sig figs for that be rounded to 2 decimals? Because it's 0.23.
Technically, yeah, they would. When it's, and once again, it kind of, this is where as long as you show your process, if your answer is varied, you're not going to get marked wrong for it. The best thing is when something is not a final step, like the final answer, I don't round sig figs till the final answer. Because it can like, because technically you don't have to do this separately, you could do it all in one big step, right? And in that case, but it shouldn't hopefully change your answer too drastically. So, good question, and you are right, it is only 2 sig figs.
Okay, this doesn't make any sense because me and Bryce plugged in the numbers into a calculator, got the same answer. We got 2.501.
And that's what I got too.
Yeah. I mean,
We have the exact same.
yeah, we have the
numbers
exact
that
same
I
numbers, and
Well, that can't be true. If you have different.
in your study?
Did you find it, Skyly?
It might be like the parentheses, because that's what happened with me.
no, because like
I did
they
it
show
once
the
without
exact
any
same
parentheses, and then I did it once with all like parenthesizing everything and everything.
Wait, did you?
What did you do
Very
different?
specific.
I don't know, I think it's the same thing.
Wait, you plugged it into his calculator,
Yeah,
but you
and I
got.
got it right.
Yeah, look, these are the same exact equations, but they give you 2 different answers.
That can't be true. Math doesn't work that way.
I know.
What is going on?
Nothing different.
You seriously.
Yeah,
What?
that's what I got
There's
too. I
seriously
keep
nothing.
putting it in. I don't know what's happening.
It's different.
I'm so no. Oh, we're all being dyslexic.
What?
114.
Oh my gosh.
Oh. That's weird that 3 of you did the same thing though.
Yeah, I put that in 114.
That's weird that 3 of you all made the same, and I couldn't even see with my own eyes for a moment.
Yeah, wait, what?
They look so identical. That I was like, math doesn't work that way.
AC Chem, yeah.
Oh, good thing we're not in like English class. We'd be in trouble. Okay, any other questions? Okay, what we're gonna look at now is the molecular side of things. So like that's kind of the mathematical, so now we want to look at and visualize what's happening at the molecular level when we make these changes, okay? What's that, Seth? It only goes every so often, so it might just be depending on what you get. It just doesn't like instantly go into skies.
Yeah, but it's like the same thing with reading.
Where'd you get your equation of very satisfying?
It's in Canvas.
Yeah.
That's probably why, it's just, it's just like, I don't
so
know when it is, but it doesn't do it like instantly, like.
Yes. Handwriting's good too.
I know.
This is why I could
It
never
sucks,
be.
always math teachers always have the worst handwriting. So they're like,
Okay, that's great. Yeah.
okay. So, for some smiley faces, here's how this works. I'm gonna give you a scenario, and I want you to predict what is going to be the change. Your answer is gonna be either increases, decreases, or remains the same. Okay? Now keep in mind, we're only gonna look at two pieces of our ideal gas equation at a time. So we're assuming that all other variables besides the two we're looking at are being held constant. They're not going to change. But if these two can change, how do they affect each other? Okay, so the first question, don't say it out loud, just write it on your paper, is if I have a system and I increase the pressure of the system, you tell me what happens to the volume of that system. So is the volume increase, decrease, or remain the same? Just write it on your paper.
Can we discuss this or no? Amongst each other.
In a moment.
Wait.
I want you to come with your own answer first. Now to help, you can think of a balloon. Because balloons have variable volume, right? Their volumes can change. Okay, so if I increase the pressure around this balloon, what's going to happen to the volume of the balloon?
Wait, around or on the
Set
inside?
volume, what would happen if you increase the pressure? And I'm like, well, the volume.
It's like
set.
I guess both have been to answer. Like,
Okay, just.
take it as the pressure outside.
Okay.
Because you can't, like,
Yeah.
the thing we're changing is like the atmospheric pressure. So what's being pushed on it.
Okay.
Good question though, because that does make a difference.
We're only talking about gases, right?
Yes. Yeah, because these things would be very different, right, if it wasn't a gas. Yes, good clarification. Okay, take a guess. Point with your finger, your guess. Increase, decrease, or remain the same. If I increase the pressure, what's going to happen to the volume? Volume will decrease. Right, speaking of the balloon, if I increase pressure,
Oh.
yeah, not on purpose, right, then the volume is gonna get smaller.
That's what I literally had an entire
Yeah, I think that's-
conversation with that.
This is why I need to pay attention.
Huh,
Well,
that's a
because
weird
both
thing
of
to
you guys
say.
thought the same thing.
So what we would say to everybody is that pressure and volume are inversely related to each other. As one goes up, the other goes down, or vice versa.
I misinterpreted
Okay.
what she was saying.
Now, thinking about our ocean of air that we live in, okay, what happens to a little child's helium balloon when it floats up in the atmosphere?
It slowly, the air around it gets, so that it gets really big, and eventually it's like BOOM!
So that's why they pop, right? And that was a really loud pop. Right? It's because as the pressure gets less, the balloon can expand more, and it only has a certain amount in which it can expand. Is anyone familiar with weather balloons? What those are?
Yeah.
Like big balloons that tell the weather.
Yeah. Really big balloons that they send up into the sky, right? But a weather balloon is built to be able to expand to crazy amounts, so that it can just keep going up and up and up and up without
So it
exploding.
senses the pressure of the air.
Yeah, because of the pressure around it. So, okay, what I want to do now in that second box is write at the molecular level what's happening. So take a second in that second box below and let's write down, we'll kind of discuss it, but I want you to write it in your own words. Okay, what happens at the molecular level? Why is this happening? Why are pressure and volume inversely related? Yeah, Evan.
So like the atoms in the air, there are more of them, so they're bouncing around. They need like their space, so they like spread out more, and it pushes on the balloon, so it gets a little bit smaller. Like that.
Say that one more time.
So when the pressure on the outside,
Okay, there we go. So the pressure on the outside increases.
then there are more atoms like moving around. Like
Okay, let me
crazy.
clarify that. Are there more atoms when I push on it? Do I make
No.
more?
They're closer together, so they have a pressure.
Yeah, there you go. There's
Okay.
right. There's more pushing, but not
Yeah.
more amount. Good.
And it's more than what's on the inside.
Good.
So
Yep. And so the volume will decrease. So very good.
How do I write that
Yeah, I
down?
know that's
We can think about the other way too if it's easier to visualize, right? So let's go the reverse. If I decrease pressure, why does volume get bigger?
Oh, because the atoms push out.
Because they can push. Think of it as a like the reason why balloons don't change right now is because the force going out is the same as the force on the inside. If there's less outside force, then the inside force can spread out. Right? Or vice versa. If there's more outside force, it's kind of like a tug of war idea a little bit. Yeah, Matt.
So like when you blow up a balloon, you're essentially like fighting the outside, like the air on the outside. So like you're putting air into a balloon and like the strength of your lungs is like giving it more pressure to fight the
Yes.
pressure outside.
Yep.
Big balloon.
Yeah, no, that's literally how it works. Is your oxygen or not oxygen, your carbon dioxide, right, is pushing out on the balloon, and that's once again also why balloons are always spherical, right? I mean, you have to like really control the shape of the rubber to try to make it not be a sphere, because that's when they're just bouncing around, right? That's the shape they're going to take. So yeah, great connection. Questions on that relationship? Now, just a side note, when you do your reading tonight, each of these relationships actually have like a law named after them. It doesn't really matter that you know the names of the laws. Like one of them is called Charles' law, one is Boyle's law. As long as you understand how they're connected to each other, though. So, just a side note in case you're worried about that. Okay, let's talk about the next relationship of temperature and volume. So let's say if I decrease the temperature of my balloon, tell me what's going to happen to the volume. Okay, so don't say it out loud, write it on your paper. If I decrease temperature, what's going to happen to volume? Okay, on the count of 3, point with your finger. 1, 2, 3. If you're pointing down, you can have a smiley face. You're like, very good. So these two we would say are directly related to each other. Right? As one decreases, so does the other. Someone feel like they can put it into a molecular view of why? What's going on there? Evan had a smiley face, by the way, for sharing with us last time. Yeah, Carly.
I just kind of thought about like what was happening like with the atoms. So when temperature decreases, the atoms start moving like slower, and like they're less likely to like bounce around. And so I just kind of pictured them like clumping together, almost like as something like freezes, they just kind of like stay close together.
Good. They start coming together, right? What she did is the biggest thing is temperature is a measurement of movement, right? So if I decrease temperature, I'm decreasing movement, which is going to decrease the force and shrink the balloon, right? You kind of get a very similar effect if you've ever left like a ball outside in the wintertime. It seems like it goes flat. It may actually not be flat. The molecules inside the balloon in the ball might just be really cold. And if you warm it back up, it actually might be fine. Yeah.
Something like with pressure, is that like when you open a yogurt, it explodes?
Wait, what? When
You know, like
open it-
pressure and volume, you know?
Yeah.
You know when like you open a yogurt, it can explode?
Yeah.
Oh.
Like, well, isn't that
You know.
because like the bacteria in it is like making gas?
See, that might be different.
Oh.
It is true. These aren't gas. Like the yogurt isn't a gas, so it's not influenced by these the same
Yeah,
way?
but there is gases in the yogurt container.
Yes.
It's like, what if they were like made in Texas or something?
Oh.
And they were brought to Utah and you open it and it explodes all over your fridge.
Oh, like,
Well, I thought it's cause like the bacteria was like creating gas, right? Cause it's eating the sugar and like.
Yeah, I know.
creating gas.
I know someone brought this up last time with like a bag of chips. Like if you have a bag of chips in California and you don't open it, and then you drive to Utah and it'll like explode in the car. Or like that same thing, like that's why you want to like pack your shampoo bottles and stuff in like a Ziploc bag, because same thing, they can kind of like explode on you. But I don't know with the yogurt. It seems like it makes sense, but it also, I'm with you too, that there are some gases being naturally made within yogurt, but I don't know how much that is. I don't know. I'll have to think about that more.
So if you put a balloon in like a really, really, really cold freezer, would it just like shrivel up, and then when you pull it out, it just expand?
So I'm gonna get some liquid nitrogen for Friday and I'll show you.
If you remember a few years ago, the Patriots won the Super Bowl, and they found that they were cheating because they put warm air or cold air in the football, and then it was cold outside or something, so it actually made it easier to catch,
Oh, so
and that's why.
I knew it was a whole thing. I don't really watch football, so I didn't see like. But like,
That
we
was
could write a whole
not-
chemistry
that was, like,
question about that
A bit more
scandal.
than a couple years ago. That was like probably a good, I don't know, but it was a long time ago.
It wasn't that long ago.
Not that long ago.
You're not that old to have that long.
But it was more than a couple years,
yeah,
a
that
couple
was
was
like,
two.
that's like, yeah,
I guess when I say couple, I don't define
I
it
don't
as two.
even.
How
a
long
couple
ago?
is like 4 or 5.
So-
A few.
Yeah.
No, a couple, I
Two
mean,
is
look,
2 or
what do you
3.
call a couple of people? 2 people, they're a couple. A couple, look it up on the internet, it is
Wait,
a
you
few.
think
A couple is a few.
Okay, take a moment, everybody, and if you didn't
Wait.
fill this box, so explain at the molecular level what's happening. Okay, so molecular level, what happens when you decrease temperature? Why does the volume change?
I have a couple of sick.
Okay, everyone good? This next one is like the most, I mean, they're all actually very logical. That's kind of hopefully what we're recognizing. If you really visualize these things, these changes make sense. But this one is probably the most logical of all of them, but I'll still give you a smiley face if you get it. So tell me, if I increase my moles in my balloon, tell me what's going to happen to my volume. Max, what's going to happen?
It's going to increase.
Very good. Why?
Because if you have the same pressure and the same temperature, and you add more stuff, then it has to.
Yeah, like makes sense, right? Like if I'm gonna blow into this balloon, it's going to get bigger, right? Unless there's something else forcing it so it can't.
Like you blow in the balloon and it like gets smaller?
Oh, like you did the opposite. Good, like it doesn't make any sense, right? Have a smiley face if you said increase, by the way.
Blowing on a balloon, so you just like squeeze all the air out of the balloon. and you'll
Now,
go-
keep in mind, this is in a sense the idea of like, this is obviously dependent on that the volume can change, right? If you add more something to something that can't change in volume, this is where you make a bomb because it explodes, right? Because it has no, if the pressure has nowhere to expand to, it can't handle the pressure for so long, right? This is why, like, if you put an aerosol can in a fire, it will explode. It's because you build up too much pressure. Don't do that. Not safe. So, okay, questions on these 3 different relationships. Okay, now let's take them and turn it back into the math side of things. Oh, side note. relationship right here gives us actually a very important conversion that we actually used on our Unit 1 test. I just told it to you, but it's through this that it works. Because of this relationship of volume to moles, Avogadro is actually the one who determined this, but he found that at standard temperature and pressure, okay, so that means at 273 degrees and 1 atm, okay, 1 mole of any gas will always have this same volume. So if I had a balloon of, if you look up there, mine got cut off, but it's on your notes, a balloon of like helium and nitrogen and oxygen, and I had 1 mole in each, they all would have the exact same volume. This is a very important conversion to go from moles to liters or vice versa. It is on your formula sheet, so you don't have to have it memorized, but know that it's there to use. Okay, let's take a look at this problem. So let's calculate some things with a balloon. Oh, it's too far. Okay, so let's say I have an inflated balloon that is 6 liters. Big balloon, okay? At sea level, so we're in California, because that sounds nice. Well, maybe nice right now, I'm not sure.
Yeah, I'm not sure it will.
Okay, we're going to let our balloon go. It's going to fly up into the atmosphere. Okay, it tells us that we're going to stop its descent at 0.45 atm. During that change, we measure that the temperature of the gas changes from 22 degrees to negative 21 degrees. We want to calculate the new volume of our balloon. Okay, so how's the volume of our balloon changed? So let's pull out, first off, circle volume, because that's what I'm trying to find. Now, the difference between this problem and the first 2 problems we did is this problem deals with a change, right? The first 2 problems we did were just, hey, calculate the pressure under these circumstances. When you're dealing with a change in factors, then we have to rearrange our ideal gas law a little bit. So the first thing you do is you take the ideal gas law as is. Okay, so write out Perfnerd on your paper.
Perfect.
The first step is to get rid of any variable that is not changing. Yeah, and
Why do we not capitalize the N? Is that just
Because the N isn't special.
my own, they just, whatever reason, the variable for moles is always a lowercase n. Trying to think,
Is it maybe because like N? Like
that's,
nitrogen?
but then like phosphorus is a P.
Oh, that's actually so true.
I don't know if it's because like the measurement of force, like a Newton, I think it's an N.
Yeah.
That
Capital
actually makes
N?
sense. That makes sense.
That's, there must be some other capital N somewhere. That's already taken. So they did lowercase.
Or
But-
someone just
yeah.
decided.
Or someone just wanted to make it small.
Yeah.
Okay, what we're gonna do is we're gonna get rid of things that are not changing in this problem.
Oh,
So what units do not change in this problem?
well, would not.
Good, so
The
cross off moles,
moles.
because the moles are not changing, so we're gonna ignore them.
And
Right.
the R.
And R, which in this case will always be canceled because it's a constant. Okay, so first step is get rid of what doesn't change. Second step is rearrange and put all the variables on one side, and we're gonna make a before and after equation. Okay, so I'm gonna move T, divide it over, so everything's on one side. Okay, so my new equation is now P1, V1, T1, that's the before, will equal P2, V2, T2. That's the after.
So it's
Nice.
that's a good time. So T divided T.
Okay, now, does everyone understand how I went from here to here? Because this is on your formula sheet, this is not. Yeah, Evan.
Why? Wait. Okay. Why does P1 V1 divided by T1 equal P2 V2 divided by T2?
It's because it's a proportion of how these things change. Kind of how we just broke them down individually, that whenever pressure goes up, volume goes down. Whenever pressure goes up, temperature goes up. So this equation combines those relationships into one thing.
Okay, and it always has to like do the same thing.
Yeah,
Okay.
yeah, because they're always going to be influenced that same way.
You can't really see the T
Up
on the
here?
screen. Yeah.
Okay, I'll write that off to the side. Thank you. I always forget because it's like right in the middle.
And it's a lot bigger than what we see, like this block.
Yeah, like the screen is like this
Oh, it
giant
moves.
sunshine.
It moves.
Okay, so cross off what is not changing. Now keep in mind, just for example's sake, let's say temperature wasn't changing here. So that means it would also get crossed off. So if temperature wasn't changing, your equation would have been P1V1 equals P2V2. Right? So you can narrow it down to just two variables, you can have three, just depending on what changes and what doesn't. Okay, let's make a list of everything we know. So I know my initial pressure was 1. So that's my P1. So P1 is all the initial conditions. The volume was originally 6 liters. And my original temperature was 22.
Alright, and now on the
So
second.
then what does it tell me is changing?
Temperature
The pressure to
and the pressure.
We got a new pressure, we got a new temperature, and V2 is the goal.
I feel like there's so many variables just to solve for one variable. If they went through all the work getting all the other ones, why didn't they just get this one?
Now let's think, well, let's do this first, then I'll ask you my question. Okay, now, once again, I like to rearrange this first before I plug things in, but you can plug things in and then solve for it. It's totally up to you. I'm trying to find V2, so I want to get that by itself. So what would be the first step to get V2 by itself?
Times T2.
Yep, so I'm going to times both sides by T2. Okay, so here's my new equation. I have T2 times P1 V1 over T1 equals P2 V2. Then, if I want to get V2 by itself, what would be the next thing I do?
Divide by P2.
Yep, so I'm going to divide both sides by P2. So that means it's going to get put on the bottom. So here's my new equation. So I have T2 P1 V1 over T1 P2
Okay.
equals V2.
P2.
Wait, why would the T2 be over the T1?
Yeah, why would it go T2?
Shouldn't the
P1?
T2 just be over the P2?
So technically when you're multiplying and dividing, it's all the same.
Oh, that's true.
So I just combine it into one. But yes, you could write it that way, but you'd get the same answer. So, based on like order of operations, right? Okay, now there's one thing you gotta do before you plug them straight over here. What do we have to convert?
The Celsius.
Yeah, you can't leave it in Celsius, otherwise you're gonna end up with a negative volume. And that doesn't make any sense. It's like a vacuum, like a black hole or something.
A black hole, exactly.
Okay, so we're gonna add 273 to both of those, and then plug it all in. I'm gonna start passing this out while you type that into your calculator. Yep.
So T2 is
P1 is 1 and then P1 is 6. Okay, let's see.
P1.
Okay, we have 1 minute left till the bell rings. So the answer you should get in the end is 11 liters.
Yes.
So what happens to the volume of our balloon. This is your homework for tonight. There are 2 questions though we haven't covered how to do that. So if you want to circle number 3 and number 5, you can try them if you want, but it deals with the equation that we didn't get to yet. It'll be in your readings, but you don't have to like understand those quite yet. But the rest of them, try them out.
Oh no, she's.
Let me know what you need help with. Check your answers.
I just noticed that
Here's your
I had all
reading.
of them.
And then there'll be a short little video to get us ready for the lab on Friday so we can get going soon, okay?
Oh, don't worry.
Whew, I think that's it. Take another Snickers on your way out the door.
We still have leftovers.